What are you guys looking for? Oh, I got put away because they used my room over the weekend for the final fire thing. Also, I'm missing like 6 calculators, so if you have accidentally wound up with one of my calculators, bring it back. They're bright yellow. If it's a bright yellow calculator that you have, you did not purchase it, they're not for sale. Those are for when you direct to schools. The amount of people still on their phones and not writing on this is a little much. So maybe I don't work it through. Maybe I just give an answer for those people that have been working, and I'll check your work when you turn it in. I don't have to go through these with you. You're supposed to work, not sit here and stare at your phone. Can we sense that I'm getting a little frustrated with this? This is using our X and box factoring. This first one, we check for a GCF. I don't have anything that can come out of 4, 12, or 9 that comes out of all of them because I can't take a 3 out of 4 and I cannot take a 4 out of 9. So we're going to do our X frame where we have our A times C at the top, B on the bottom. We should wind up with our X frame looking like this. What pair of numbers do we get that multiplies to be 36 and adds to be 12? 6 and 6. So when we fill in our box, we have our 4x squared and our 9 from our equation. Then we're going to grab our 6x and our 6x from our x frame. They get whatever this middle variable is. And they come from these numbers. When we pull our factors, what are we getting? Mm-hmm. Mm-hmm. And the other one is? 2x plus 3. So we can write this in a couple of different ways. You can write it as 2x plus 3 times 2x plus 3. Or since they are 100% exactly identical, you can put this as 2x plus 3 squared. Either of those would be a fine answer for this, to factor it. Either way is fine. Yes, sir. A times C, 4 times 9. This was our A, B, and C. Always put our AC on the top and our B goes on the bottom. You can do the bottom one exactly the same way. 100% exactly the same way. We can also start to notice this one is one of our special patterns. 9 is a perfect square and 25 is a perfect square. So I have 2 things that are perfect squares and we're taking a difference. So you can do this through the full box just as it is, or you can remember that this is our difference of perfect squares. Yes, dear? also does not have a GCF because 25 is not divisible by 3 or 9, and 9 is not divisible by 5. So I don't have anything I can take out of both of them. You have to look at each piece. Since 9 and x squared are both perfect squares, and 25 is a perfect square, that's when we know we can use the difference of squares pattern, which we know is going to have 2 parentheses. What squared gives us 9x squared? 3 and x. So we're going to put a 3x in the front of both parentheses. What squared gives me 25? 5. So those goes on the back of each of the parentheses. One gets a plus, one gets a minus. 3x plus 5, 3x minus 5. So you absolutely can still use the box on this. You just have a b of 0. It's totally fine, but it is going to take longer. And we are going to be factoring a bunch in this chapter, so starting to recognize some of the special patterns is good for us to practice, like the difference of squares. We will have difference of squares show up for both. Questions on either of these? Okay. Because what we're going to start working with are going to be equations and expressions that have these kind of guys. My 4x squared plus 12x plus 9 on the numerator of a fraction and something like it in the denominator. So we're going to have quadratics in fractions. And they are called rational expressions. And these have more steps sometimes than like the logarithms did, but I feel like this is not as foreign as the logarithm, because the logarithm feels kind of like magic when we start out with it. So this is made up of things we've all done. We're just stacking them up in weird ways. So we've got that a rational expression is a ratio of 2 polynomials. What that is typically going to look like, a ratio means it's going to be a fraction. And polynomial expressions are all the things we've been working with. The x squared plus 2x plus 3s, x minus 7, all of those pieces. We could even have exponentials in there. We're not because they're super gross, but we could. Anything that's a polynomial can be inside our rational functions. And since we've been working with factoring, we've worked with simplifying, we've worked with exponential situations, we're going to be able to use a lot of the same operations on fractions for rational expressions that we would do for regular fractions, number fractions. So looking right here, they're looking at simplifying this fraction where it was 35 over 45. So what they did was they broke it into multiplication, because I can rewrite 35 as 5 times 7, and I can rewrite 45 as 5 times 8. So they factored it to simplify it down to 7/8, because there's the same thing in the numerator and the denominator. So this is like how we simplify fractions. Since they both can divide by 5, we divide both by 5. We can do the same thing with rational expressions here, and this is what we're going to be starting with today, is we're going to take pieces like this. This is going to be a problem like ones we have, where we have x squared plus 7x plus 10, and we could factor it. it would give us x plus 5 times x plus 2. We could take this x squared minus x minus 6 in the denominator, factor it with the x in box. It'll give us x minus 3 and x plus 2. Since there was an x plus 2 in both the numerator and the denominator, they can cancel out. Just like we canceled out the 5's up here. Since it was the same top and bottom. Since it was the same top and bottom, we can cancel it out. Notice how we did not do any canceling over here when things were being added together. We can only cancel out when it is multiplication. We can only cancel out multiplied terms. That's it. Okay, so we're going to start with working with some rational functions and simplifying some of these fractions. It's going to start out very, very familiar with some very similar pieces here. We've worked problems like this before. But there's one more funky thing we're going to need to remember. So when we start with something like 6x squared over 15x to the third, we're going to come in here and try and simplify this. So think of this as like a regular fraction here. What can we simplify with 6x squared over 15x to the third? Three. I can divide 6 and 15 by 3. I'm going to write it the way they did in the example over there. So I can rewrite 6 as 2 times 3. And I'm going to leave that x squared. And I can rewrite the 15 as 5 times 3. And I can rewrite my x cubed as x squared times x. I haven't changed anything here. I just rewrote stuff. Because since I have the same thing top and bottom, they eliminate out. These two pieces simplify down to be one when they're the same top and bottom. What else can eliminate out? The x squareds. So the only thing I have left on the top is a 2. And the only thing I have left on the bottom is 5 and x. Do we know what x is or what x equals? That one? No. Because when we go to like graph this, we're going to plug pieces in. We're going to substitute things in. So what is the one thing that's going to give me a glitch in the calculator when x equals? What's the one thing we can never, ever, ever divide by? 0. If you go on the calculator and hit 2 divided by 0, it's going to say domain error. We can't divide by 0. So we're going to have a lot of expressions in this chapter where we have rules upon our domain simply because we can't divide by 0. So that's what this statement at the bottom says, is the expression is undefined when the denominator is equal to 0. So when I'm going to take my OG denominator, this guy. 15x cubed is equal to 0. When is 15x cubed equal to 0? What would x be? 15 times what is 0? 0. So in our answer, if we were to be trying to do more with this and solve it or graph it or do anything crazy with it, x cannot be 0. We cannot divide by 0. So we're going to be doing a lot of simplifying fractions and finding rules for our denominator, because our denominator cannot be 0. Questions on this first one? Okay. The next one's going to be a little bit weirder. All right, so I have a fraction that on my numerator has x minus 4, and my denominator is x squared x squared minus 7x plus 12. No matter what, the first thing we're going to see is whenever we have adding and subtracting in the denominator, we're going to come through and we are going to factor any piece that has an x squared. If it's just like an x minus 4, we can add just parentheses around it, just so that we remember that's a piece. And we're going to factor this x squared minus 7x plus 12. So I'm going to bring it over here. We're going to fill in our x frame, just like we did for the bow work, where we put our a times c on the top and our b goes on the bottom. What is our a value? 1. What's our c? 12. So a times c is 12. Our b is negative 7. So we need a pair of numbers that multiplies to make 12 and adds to make negative 7. Negative 4 and negative 3. So we're going to factor the whole thing. We're going to take our x squared from our expression up here and our 12 from our expression. Then we're going to have our minus 4x and our minus 3x. So then we're going to pull our factors, columns and rows. And what are our factors for this one?
X negative 4 and x negative 3.
X minus 4, x minus 3. So I can rewrite this whole fraction up here using my factored forms, where we're going to have our x that was minus 4 on the top, and my factored form turns into x minus 4, x minus 3. What do we notice about our factored form over here? X minus 4s can cancel out. I have the same piece on the top and on the bottom. So they cancel out. Those simplify down to just be 1 because they're the same top and bottom. So since they simplify down to just be 1, we're left with 1 over x minus 3. Questions on that part? Because I know these are a little weird. Yes, sir. Yeah, give me a second. So then we also need to keep in mind that there are going to be places where this whole thing doesn't work. And so what we're going to do is we are actually going to come and grab the factored form equation for our when the denominator doesn't work. So our expression is undefined when each of those pieces would equal 0. So when x minus 4 equals 0, or when x minus 3 equals 0. Just like when we were solving quadratics, it's any of the pieces equal 0, then it makes the whole denominator 0. Because if that chunk was 0, it would be 0 times x minus 3. If the other chunk of 0 would be x times, or 0 times x minus 4. So where does x minus 4 equal 0? When does my denominator equal 0? When x is what? 4. When else does my denominator equal 0? And 3. So the expression is undefined at x equals 3 and at x equals 4. Questions on that one? Okay. That's kind of the vibe with what we're doing today. So here's another one. So we have x squared minus 2x minus 24 over 2x cubed plus 6x squared minus 8x. So first thing we're going to do is we're going to come through and try and factor each of these. So I'm going to start with my numerator. I'm going to take this guy and we're going to go left. We're going to build our x and our box so that we can kind of factor. As a wonky box, but we get the gist. What's going to go on the top up here? 24. Is it positive or negative 24? Negative 24. What goes on the bottom? Negative 2. What is our pair of numbers that multiplies to make 24, or multiplies to make negative 24 and adds to make negative 2? Negative 6 and positive 4. So when we fill in our box, we have our x squared and our minus 24 from the equation. And then we're grabbing our minus 6x and our positive 4x. And we're going to pull our factors in columns and rows. And what are they going to be?
X negative 6 and x 4.
Yep, x minus 6 and x plus 4. And we don't put an operation in. Its default state is plus. So we can rewrite this into factored form. This is the same thing as x minus 6, x plus 4. Then we're going to take this guy, and we need to factor it. Since I have an a value here, we need to check for a GCF. Does this have a greatest common factor amongst these pieces? What does it have in common between all three? 2. Anything else in common between all three pieces? X. They all have x's. So we can factor out a 2x from each of these. 2x cubed divided by 2x gives me x squared. 6x squared divided by 2x gives me plus 3x. And minus 8x divided by 2x gives me minus 4. So watch out for times when they put GCFs of letters. There can be a letter in your common factor. Yes. I took each of these original terms and I divided it by what we saw in common. So 2x cubed divided by 2x is x squared. 6x squared divided by 2x is 3x. 8x divided by 2x is minus 4. But this isn't fully factored, so we're going to have to come through and we're going to do the x and box on this piece. So we're going to take our a times c, our 1 times minus 4, and that's minus 4. My b goes on the bottom, it's a positive 3. What is a pair of numbers that multiplies to make a negative 4 and adds to make positive 3? 4 and negative 1. So when we come in here to put this through our box, we have our positive 4x and our minus 1x. When we pull our factors here, what do we get? X squared and minus 1x share an x. 4x and minus 4 just share a 4. X squared and 4x share an x. And minus 1x and minus 4, they share a minus 1. So when we're writing out our factored form, we're absolutely going to take those two factors from our box, our x plus 4 and our x minus 1. We also need to come grab our GCF over here that we pulled out before we factored. So that 2x is still a player over here. So we're going to need to factor the top, factor the bottom as far as we can. We need to get it down to all things that are being multiplied. Yep, that was the next thing I was going to say is what do we have that is the same top and bottom? It's that x plus 4. So with that x plus 4 being the same top and bottom, these guys can cancel out. Yes, dear.
Is the 2x like with the x plus 4 on the bottom?
It's still being times. So if it helps, you can still put parentheses around it. It just doesn't make any difference because there's not any addition going on. So our simplified answer is going to be the pieces that are left on the top. So my x minus 6. And my denominator is going to be the 2x times x minus 1. And that's going to be how we write our answer. This guy. Then the instructions will often say something like state the excluded values, the pieces that don't fit. And what that is saying, all right, when does my denominator equal 0? I want to know when my denominator equals 0. So I want to know when 2x equals 0. I want to know when x minus 4 equals 0. And I want to know, oh, I'm sorry, that was x plus 4, excuse me. And x minus 1 equals 0. So we take all of the pieces from our factored form, and those are what's called our excluded values. So this is going to have 3 of them, because there's 3 chunks down here. 1, 2, 3. So when does 2x equal 0? What do we do to get x by itself? Divide by 2. What's 0 divided by 2? 0. I have no cookies to split among my 2 friends. So x equals 0 is one of our excluded values. How about for this one? X plus 4 equals 0. Minus 4. And how about for x minus 1 equals 0? Plus 1, positive 1. So our denominator equals 0 when x equals 0 or 1 or negative 4. Okay, so we're going to be doing a bunch of factoring. Yes, dear.
Is it always going to be x equals 0? Like is one of the...
It's actually, we're only going to have x equals 0 when we have a GCF that includes x. It's always going to be when our terms in our factored form equal 0. So having an excluded value of x equals 0 is going to be actually kind of rare. What do you mean? Be more specific. So if it didn't have this GCF, if we just started with that, it would just lose this piece and everything else would have been exactly the same. So let's do one more, just so we can see this again. Okay, this will be our last one. Because honestly, they're going to usually be more like this, where they're just x squared over x squared. So we're going to factor the top, we're going to factor the bottom, we're going to see if anything cancels out, and then we're going to find our excluded values. So I'm going to take my numerator, that piece on the top, and we're going to factor it. So we're going to set up our x and our box, where we have our a times c, 1 times 1, which is 1, and our b, which is 2. So we need a pair of numbers that multiplies to be 1 and adds to be 2. One and 1. So we take our x squared and our 1, and we're going to have our 1x and our 1x. Pull our factors in columns and rows. What do we get? We're going going to have x plus 1 and x plus 1. So our factored form on this piece is x plus 1 times x plus 1.
Could you write that x plus 1 squared?
You could. It's just going to be a little trickier when we go to cancel things out, remembering that it's got that exponent there. But you can absolutely write that as x plus 1 squared. You're just going to have to be careful when you simplify. So then let's do our denominator. This one. And it's the same thing. We're going to x and box it. So we have our 4x squared plus 3x minus 1. So my a times c, 4 times minus 1 gives me minus 4. And my b is a positive 3. What is a pair of numbers that multiplies to make negative 4 and adds to make positive 3? 4 and negative 1. Love that. So when we go into our box, we're going to have our 4x squared from our equation and our minus 1 from our equation, getting our 4x and our minus 1x. When we pull our factors in columns and rows, what do we get? X plus 1. It's the only thing they have in common. And 4x minus 1. So our factored form up here is x plus 1 and 4x minus 1. Can we simplify this? Yes, because I have an x plus 1 on the top and I have an x plus 1 on the bottom. So this piece cancels out with that piece because they're exactly the same.
What about those two?
We can only cancel out one at a time. I can't cancel out both. It's not like card games or something like that. We can only take one on the top, one on the bottom. So our answer is going to be x plus 1 over 4x minus 1. Questions on that part? Okay, our last piece here is this whole thing is undefined when our denominator equals 0. So we're going to take all the pieces in our denominator and set them equal to 0 to figure out where x cannot be. So we know that x plus 1 equaling 0 is a problem for me. And we know that 4x minus 1 equaling 0 is a problem. So on this one, what do we do to figure out our undefined place? Subtract 1. So we're going to have x equals minus 1. So that's one of our problem zones. So x cannot equal negative 1. Or what are we going to do on this one? Add 1 and then divide by 4. So we'll have that 4x equals 1 and then x equals 1/4. So x cannot be negative 1 or 1/4. Okay, so it's kind of fiddly, kind of weird, doing weird things, and making strange choices. I love when people do this stuff. That makes me so thrilled. Okay, so I'm gonna pass out homework 1 for this chapter. You can actually do everything on it right now. It is factoring and then what we did today. Okay, so we can do everything on this. And then I'm gonna get announcements up on the board. I have a feeling that happened a lot. They were feeling very staticky this morning, so yeah. All right. We are going to be having a chapter quiz on March 27th, which is the Wednesday before spring break. And then the test for the whole chapter will be after spring break.